Hey everybody, welcome back to another video. So today's video we're going to briefly talk about ethyl alcohol metabolism and what are some of the complications that chronic high alcohol usage can cause. So if you guys like the video, if you learned something from it, if you truly enjoy it, consider liking, consider subscribing, and maybe leaving a comment. Without further ado, let's get started. So, ethyl alcohol, or more often called ethanol, okay? Once you eat it, right, and after it gets absorbed, which by the way, it'll be absorbed through the entire of the GI tract, and because it's very lipid soluble, it can easily be transported through the enterocytes and come inside of the bloodstream completely unaltered. And this ethanol can be toxic in ranges of 50 to 80 milligrams per DL, right? So this is the toxic range of it in the bloodstream. This is where intoxication can occur. And about 80% of the ingested alcohol reaches the liver, right, where it'll come in contact with the hepatocytes, right, the liver cells. And the remaining 20% will go to other tissues, again, including the brain, right? That's where you kind of experience a lot of the, loss of coordination, balance, and like sleepiness that you will experience. Now, nutritional-wise, alcohol gives you about 7 kilocalories, but these calories, right, we call these empty calories because really when it comes to alcohol, not only does it not give you any beneficial micronutrients or macronutrients, right? It also, in long term, kind of impairs the metabolism of other ones, such as like vitamin A, and we'll talk about that. But it gives you about 7 kilocalories, right? So it is pretty filling. You guys know the fat gives you about 9 kilocalories, and then carbohydrates gives you about 4 kilocalories, right? We'll have a video on this when we talk about energy balance, probably the next video. Now, when it comes to alcohol, for moderate users, about like 10% of their total energy intake is alcohol, and for alcoholics, it's about 50%. Again, these are just estimates. But again, what actually happens when this ethanol actually reaches the hepatocyte, right? Because we said 80% of the metabolization actually occurs in the liver. So let's show this ethanol actually coming here. And it can go into 3 different routes. Okay, it can go 3 different routes. So the first place that it can go into would be the cytosol. Okay, and when it comes into the cytosol, let's draw it here. So here is our ethanol. Okay, this ethanol can be converted into a molecule called acetaldehyde. This guy is bad news. Acetaldehyde, not what you want being generated, okay? And I'll tell you why in a second. Now, there is an enzyme that actually converts this ethanol into acetaldehyde inside of the cytosol. And that one's actually called alcohol dehydrogenase, okay? Alcohol dehydrogenase. You can also find this in the gastric mucosa as well. The alcohol dehydrogenase, it has a relatively high Km, as compared to any of the other enzymes that we'll talk about when it comes to oxidizing ethanol. And it has a Km of about 1 millimoles, or you can call it 5 milligrams per DL. Okay, what does this actually mean? This means that this enzyme has a high affinity for oxidizing ethanol, but doesn't have too high of a capacity for it, right? So remember I told you that the circulating level of 50 to 80 milligrams per DL can be toxic. Well, upwards of 15 to 24 milligrams per DL can fully saturate this alcohol dehydrogenase enzyme, and it cannot handle any more ethanol coming its way to make this acetaldehyde, and thus we have to use another pathway inside of this hepatocyte for oxidizing the ethanol, right? Now, one thing I should mention is that during the process of converting this ethanol into acetaldehyde, this enzyme also uses NAD. Okay, NAD positive, right? Which you guys know is coming from niacin, right? The vitamin. Okay, so one more time, this ethanol, with the help of alcohol dehydrogenase in the cytosol, will take this ethanol and the NAD positive, and it'll make acetaldehyde and NADH. And I said that this enzyme has a relatively high Km, which means it's got higher affinity towards alcohol, but it has a low capacity, meaning that it can't handle too much ethanol coming its way. And we said it gets saturated at around 15 to 24 milligrams per deciliter, right? So in the intoxication levels, this enzyme is for sure saturated. Now, the other thing that we should talk about is, okay, so if this guy is saturated, what is the next pathway that we can use? Well, if we turn our attention towards the smooth endoplasmic reticulum, okay, we'll see that ethanol can also make its way into the smooth endoplasmic reticulum, right? This is the second pathway that's used after we've kind of run the course with the alcohol dehydrogenase. And you'll find here that ethanol can also be converted into acetaldehyde, okay? But something different occurs. The enzymes that are involved here are actually not just one enzyme. There are a group of enzymes that are collectively called the microsomal ethanol oxidizing system, okay? The MIOS for short. This also has another name called cytochrome P450, okay? Again, cytochrome P450 is not just one enzyme, okay? It is a group of enzymes that are involved in the metabolism of many things, okay? So, for example, metabolizing ethanol, fatty acids, aromatic hydrocarbons, right? For example, polycyclic aromatic hydrocarbons can be found a lot in like meats, steroids, and a lot of drugs, right? There's different cytochrome enzymes. And the enzyme that is really specific here in metabolizing ethanol to acetaldehyde, if you really want to know, is actually cytochrome P2E1, okay? And it has been estimated that about this MIOS is responsible for about 20% of ethanol oxidation, okay? So you can see that the alcohol dehydrogenase is responsible for like 80%, maybe even more, whereas the smooth ER microsomal ethanol oxidizing system is responsible for about 20%. Okay, I'd say upwards to 30% as well for alcoholics. And the other thing you should know is this pathway is very much inducible. What do I mean by this? I mean that excess alcohol consumption can actually lead to the upregulation of many of the enzymes involved in this MIOS pathway. And that could actually lead to alcohol tolerance. And what this means is, over time, you would actually have to drink more alcohol to essentially get drunk, okay? And that's why a lot of people that are heavy drinkers as compared to lighter drinkers experience, different kind of tolerances and intoxications. There are other things we can talk about. For example, the fact that on average, again, women have a lower tolerance to alcohol than men, which, again, it could be due to many reasons, to be honest. It's been said that they have lower ADH levels. It's been said that because of the smaller liver, they can't metabolize as much, right? So it's many reasons. The other important thing about the liver, by the way, is that it can only metabolize about 1 ounce of alcohol per hour. Regardless of the amount consumed, okay? And 1 ounce is about 30 milliliters. And you can see it's not that much. So a light beer has around like 355 milliliters. And metabolizing, 30 mLs in 1 hour? Yeah, you're definitely going to exceed the amount that the liver can metabolize in 1 hour, right? So that's how... you can get drunk pretty fast. Now, to carry on with some of the, constituents of the reaction here, ethanol to acetaldehyde using the Meos system uses special kinds of molecules. It doesn't use NADH. It actually uses something called NADPH, right? And it actually uses all of these stuff, NADPH, and it converts the NADPH into NADP, right? Plus 2 waters, actually. Okay, 2 waters. So this is the kind of reaction that's occurring in the smoothie yard to generate this, right? And I can go into more detail on this, right? For example, there's flavoproteins involved, like FMN and FAD involved in this reaction. But again, it's not a biochemistry video, so we won't kind of go into that much detail. The last one that can occur, and I debated about whether I should put this in or not, but it's good to know all the details, is that the ethanol can go into the peroxisome, right? Where ethanol can again be converted into acetaldehyde, okay? Aldehyde. But in this scenario, there is a special enzyme in here called catalase, okay? It's called catalase inside of the peroxisome, and that's the enzyme here. And he's going to convert ethanol into acetaldehyde with the usage of, again, something very weird. It's using reactive oxygen species. So it's going to turn hydrogen peroxide into water during this reaction of ethanol to acetaldehyde, okay? So that's how that's doing that. And in individuals that actually have a normal functioning, ADH and stuff, they've found that it's responsible for less than 2% of ethanol oxidation, right? So that's why this guy doesn't get talked about too much. Now, of course, its activity is higher in organs where you don't have the ADH, right? For example, the brain. In the brain, you don't actually have alcohol dehydrogenase, so the activity of these two is higher. Okay. Next things. Now we're going to kind of actually look at what happens where we're forming this acetaldehyde, right? So all these guys are forming acetaldehyde, right? So let's take bring all these guys here, right? We formed acetaldehyde from ethanol in these 3 pathways, right? These two being the main 2 pathways. This one's in the cytosol, this one's in the smoothie R, and if you want, this one's in the peroxisome. Now, let's bring this acetaldehyde over into the specialized organelle called mitochondria, okay? The mitochondria, man, look at them. The acetaldehyde levels, acetaldehyde. There we go. Okay, what's going to happen to this acetaldehyde? Okay, inside of the mitochondria, right, the acetaldehyde will actually be turned into acetate, okay? And that's actually catalyzed by a specific enzyme. Again, that enzyme is called aldehyde dehydrogenase, okay? Aldehyde dehydrogenase, and if you want, it's specifically aldehyde dehydrogenase type 2, okay? Now, again, this reaction is also taking NAD positive and turning it into NADH. Okay? Now, this acetate, it can actually leave and go to organs like the skeletal muscle and be turned into acetyl-CoA, but it can also turn into acetyl-CoA here inside of the liver, right? So here, it can be turned into acetyl-CoA, and this honestly requires only one thing, which is the addition of a coenzyme A. Okay? It only requires a coenzyme A to be added in here and to make acetyl-CoA. Okay. Now, something I want to point out here. Is, what do you notice? I said, of these 3, which one is the most utilized to oxidize ethanol? I said ADH is the most utilized, right? And when this guy goes through this reaction a lot, what happens? What happens to the NAD and the NADH ratio? The NADH levels start to build up in the cell, and the NAD levels are depleted. They start to go down, right? Because I'm continuously going through this reaction. This increase in the NADH to NAD ratio is a signal to the cell. It's a signal to the cell that's saying, hey, we're having a lot of oxidation reactions occurring. You should probably shift the balance to a reduction / hydrogenation. Okay? That's what it's saying. Okay, but what does it actually mean? Let's take a look at it. Okay? And by the way, where are we making lots of NADH? We're making NADH here, and we're making NADH here. So let's say if we didn't even take this pathway and we took these other two pathways, we'd still be making a lot of NADH, okay? But either way, we make a lot of this NADH, all right? What happens, and what implications is high NADH actually going to have? I'll mention that in a second, but briefly, I just wanted to talk about acetaldehyde and why it can be extremely toxic. Acetaldehyde can be just as toxic, if not more toxic, than ethanol, because it's actually very highly reactive, and it can actually bind to proteins, nucleotides, and phospholipids through covalent binding, and it can form adducts, okay? An adduct is literally just when these two molecules are bound together, okay? So imagine I have this kind of, enzyme here, okay? And this enzyme is responsible for a specific reaction, all right? Now, if I have this acetaldehyde, right, accumulating acetaldehyde, and let's just say it'll come and bind to this guy, it can disrupt or completely stop the function of this enzyme. Now, you can imagine how bad this can be when acetaldehyde might make its way into the bloodstream. For example, you have hemoglobin. What does hemoglobin do? Hemoglobin transports oxygen, right? It's supposed to bind oxygen and release it on the tissue and bind CO2 and then release it there as well into the alveoli. So once acetaldehyde binds to this hemoglobin, its function is completely annihilated. Okay, it can no longer transport oxygen, right? And acetaldehyde, man, it's highly reactive. That's why it can bind to all of this stuff. It can also enhance other things, like it can enhance lipid peroxidation and thus promoting free radical damage. So, not good. Not really good at all. Okay? Not good. And, it's not just proteins and fats and all this stuff, right? I did mention it can bind to nucleotides as well, right? So it can cause DNA damage, which might lead to cancer, right? So, but, a majority of the studies have shown that acetaldehyde is highly correlated with hepatic cirrhosis, so liver scarring, and also liver fibrosis, right? And so that's not really good at all, because once the liver actually starts becoming fibrotic and cirrhotic, right, it actually loses a lot of its main functions, which are just, a lot of things actually. The metabolism of drugs, metabolism of a lot of the macronutrients, right? We know it's involved heavily in glucose metabolism, fatty acid metabolism, cholesterol metabolism, and protein metabolism by going through the urea cycle, by doing transaminations, by producing a lot of plasma proteins like albumin, like transferrin, like blood coagulation proteins, or C-reactive protein, or all of these things, man. Liver is so involved, and honestly, I'll probably make a video on the liver sometime soon. Now, just to get back to our conversation, acetaldehyde, toxic, can form adducts, not good, okay? Because the adducts impair the function of that thing that the acetaldehyde bound to. Now let's go to the high NADH. I said the high NADH is coming from oxidizing ethanol through the ADH pathway, and from the acetaldehyde being turned into acetate via aldehyde dehydrogenase 2 inside the mitochondrion. What does the high NADH do? Okay, so in order to understand this, we got to understand a little bit of biochemistry for a second. So this acetyl-CoA, right, what can it usually do? Usually, inside of the mitochondria, the acetyl-CoA, right, will combine with something. It'll combine with a specific constituent of the Krebs cycle called oxaloacetate. And when the oxaloacetate and the acetyl-CoA combine, they make a molecule called citrate, okay? Now, citrate will continue onwards, right? And it'll make molecules such as alpha-ketoglutarate, right? And, there's other ones involved, like malate, for example, right? And then OAA. I didn't put the entirety of the Krebs cycle here, but you get it, right? It'll go through the Krebs cycle. What I want you to focus on mainly, right, is the citrate, okay? That's the citrate. So when we go through this process of the Krebs cycle, we actually make a lot of citrate because of this high acetyl-CoA. So remember, we were making a lot of acetaldehyde, and this reaction, right, in order to get rid of this toxic acetaldehyde in our body, was making acetate. And the acetate can be converted to a lot of acetyl-CoA. The acetyl-CoA, when it builds up, right, you know what it can do? It can go into the Krebs cycle. But here's where the high NADH comes in. You know, inside of the Krebs cycle, we actually make a lot of NADH as well. Okay? We make a lot of NADH. But if I already am making a lot of NADH from alcohol metabolism, you know what that's going to do? That's going to come to the Krebs cycle and inhibit it. It'll slow down the Krebs cycle activity. It'll say, hey, man, I've already made a lot of NADH here. You don't need to keep making NADH. So it'll stop its activity. Okay? And if we slow down the activity of the Krebs cycle, right? For example, by preventing some of the dehydrogenase reactions, like here or here, right? You know what's going to happen? A lot of this citrate will start to build up. And we had a lot of acetyl-CoA, which was going to combine with this OAA to make citrate. So we actually have a lot of citrate building up right now. You know what's going to happen to this citrate? This citrate would actually leave the mitochondria, right? It'll be exported out of the mitochondria, and it can be pushed into a pathway of making fat in the liver. How does that happen? Well, this citrate here comes out, right? And it'll be acted on by specific enzymes, right? To make acetyl-CoA, okay? And then this acetyl-CoA, right, again, will be acted on by further enzymes, which can eventually put it towards the pathway of de novo lipid synthesis. Okay, so de novo lipid synthesis stands for making fat. Okay, making fat out of nothing, out of scratch. And look at this, we're gonna build some fatty acids. And these fatty acids can actually be incorporated into the lipid droplets or the fat storages of the liver, right? Which is primarily triacylglycerides. You guys should know that. And this can actually, if this pathway occurs excessively, which it does in an alcoholic, it can actually lead to liver or hepatic steatosis, which is just fatty liver. Okay, this one's alcoholic fatty liver disease. And you guys know, by the way, that this fatty acids, they can also be put out either just as NEFAs, right, non-esterified fatty acids bound to albumin in the blood, or they can be put out as VLDLs, okay? And depending on which stage of hepatic steatosis you are, the VLDLs might be high or low, right? It just differs. Okay, now, that was why the high NADH mattered. The high NADH said, hey, let's shift our body to more reduction reactions so we can kind of regenerate more NAD positive, okay? And believe me, when you start doing all this, you will regenerate more NAD positive, okay? So let me give you a couple of examples. Now, I'm going to go into a little bit of extreme detail here. So for those of you who don't need to know too much on this, I'll just kind of say the implications of alcoholism. But for those of you who either enjoy it or need to know it, feel free to stick around. So the symptoms, or I should say the implications of alcoholism, okay? What can it actually lead to? Well, it can lead to fatty liver disease, right, which we talked about. It can lead to fatty liver, one. The second thing it can be is it could possibly lead to ketosis, and we'll talk about how. It can lead to hypoglycemia. So hypoglycemia, and again, we'll talk about that. And it can lead to hepatic cirrhosis, which we talked about, right, because of the high acetaldehyde, right, cirrhosis. And yeah, so these are the things that it can lead to. Again, there's other things, like, for example, it can lead to esophagitis or gastritis, right? And, you know, we also talked about the brain damage and the cognitive function impairment that can occur, but we'll stick to kind of these metabolic implications here. Now, we're going to take a look at how all this stuff comes about, right? So we talked about fatty liver, we talked about hepatic cirrhosis, right? So that's great. Let's knock those off the list. But how does ketosis and hypoglycemia, and I'll add a couple more here. So lactate acidemia, lactate acidosis, and there is another one. There's vitamin A deficiency as well. This can also happen. So vitamin A deficiency. So we're going to talk about this guy, this guy, this guy, and this guy in biochemical detail. Okay, so let's go through it. So first things first, let's talk about lactate acidosis. Lactic acidosis. So in order to understand this, you got to understand glycolysis, right? So you guys know that we start out with G6P, and then we go into fructose 6-phosphate, and then we go into fructose 1,6-bisphosphate, which can then be turned into glyceraldehyde 3-phosphate, and then they can be turned into DHAP. You know, these guys can isomerize with one another. The DHAP can then be turned into other things, such as 1,3-bisphosphoglycerate, then it can be 3-phosphoglycerate, and then 1-phosphoglycerate, then phosphoenol pyruvate, and then pyruvate finally. So through glycolysis, right, I take glucose, and I make pyruvate. Now this pyruvate usually will get turned into acetyl-CoA, right? But in the presence of a high NADH to NAD ratio, you know what ends up happening? What ends up happening is there's an alternative reaction where pyruvate can turn into lactate, right? And that requires a specific enzyme. That enzyme is called lactate dehydrogenase. There's different isoforms. But this lactate dehydrogenase, right, it's a reversible reaction, right? It can go in either direction based off of the concentrations. Now, when I have high pyruvate, right, and I also have a high NADH, you know what's going to happen? The NADH will participate in this reaction, okay? And it'll actually convert the pyruvate into lactate, okay? So now I will actually have high lactate levels, okay? Because the alcohol metabolism increased my NADH to NAD ratio. And what did I say? When the NADH to NAD ratio increases, the body receives a signal that says, hey, I'm going through a lot of oxidation reactions, and I need to go through a lot of reduction reactions to regenerate my NAD positive. And that's what we just did. We regenerated NAD positive, but we also made a lot of lactate. Okay? So that's not good. What are some other ones? What are some other ones that we can kind of think of? Well, you know, within the actual Krebs cycle, right, we are actually going through some reactions ourselves, right, where we're producing NADH. So remember, we said NAD positive here, right? Go to NADH, right? It can also be done here, for example, right? NAD, right, to NADH, right? But remember, I said that all of this stuff will be disrupted because we already had high NADH levels, right? So Krebs cycle will be disrupted as well. What else can I talk to you about? So we talked about the lactic acidosis. Let's knock that off the list as well. Let's talk about ketosis. Ketosis, in this case, is kind of relatively simple. When you have all of these high acetyl-CoA levels, because of the high acetaldehyde being converted into acetate and the acetyl-CoA, right? There is a possibility where you can go through ketone production, because, you know, acetyl-CoA can actually be turned into ketone bodies through a series of reactions. For example, you can turn acetyl-CoA into acetyl-CoA, right? And then make ketone bodies eventually. But a couple of parameters have to be met. So first things first, you have to have a high NADH ratio, which we do. But the other thing that has to be met is you also have to have a low carbohydrate diet or low carbohydrate availability, like glucose availability. And you also have to have high amounts of acetyl-CoA, okay? High amounts of acetyl-CoA. So you can clearly see, right, these three have to be met. And in this scenario, only two are being met, okay? So there is a potential for ketone production, all right? There is a potential for ketosis. Okay, so that's going to cross off ketosis off the list. The other thing is hypoglycemia, and you guys should remember that the liver is the main site of gluconeogenesis, where we actually maintain blood glucose levels. So how come there might be hypoglycemia occurring here? Well, this special intermediate in the Krebs cycle called alpha-ketoglutarate, this guy can be used in a lot of transamination reactions, right? And I'm sure you guys have heard of amino acids such as alanine that can be used for gluconeogenesis. You know, alpha-ketoglutarate, it can actually give us alanine. It can actually be transaminated to give us alanine. It can also give us another amino acid that can be used for gluconeogenesis called aspartate. Okay, that's another one, right? And both of these guys can be used for gluconeogenesis, GNG abbreviation. Now, why do I say that this has anything to do with hypoglycemia? Well, remember, alpha-ketoglutarate can give us alanine and aspartate, and both of them can, give us blood glucose levels, right, through going through gluconeogenesis. But when you have a high NADH to NAD ratio, you know what happens? There is a reaction that alpha-ketoglutarate goes to, right, where it can be turned into glutamate, the amino acid glutamate. And that's driven by a specific enzyme called glutamate dehydrogenase. And guess what, man? Guess what? This glutamate dehydrogenase, it takes NADH and converts it into NAD positive, right? That reduction reaction that we were looking for to restore homeostasis. So because of the elevated NADH to NAD ratio, I'm actually depleting my levels of alpha-ketoglutarate. And if I have low amounts of this, I have low amounts of this, and I have low amounts of this, which means I will have low amounts of gluconeogenesis, which means my blood glucose levels will start to go down. Okay, I might become hypoglycemic. So that is another possible condition. And then finally, the last thing we'll talk about is going to be the vitamin A deficiency. Okay. Oh, before we talk about that, actually, let me add on something into the liver steatosis. So a lot of you might be thinking, okay, we had the fatty acid coming from the de novo lipid synthesis, but where's the glycerol coming from? In this same Krebs cycle, right, we actually make this product here called glyceraldehyde 3-phosphate. This GA3P can actually be turned into something called glycerol 3-phosphate. That's the glycerol that we're going to use. How did we get there? There's an enzyme that does this. It's called glycerol phosphate dehydrogenase, right? Glycerol 3-phosphate dehydrogenase. And guess what? This reaction, it takes NADH. It takes NADH. So again, the high NADH not only drives high acetyl-CoA levels, right? Sorry, not the NADH levels, the high NADH levels, right? They not only slow down the Krebs cycle to elevate the citrate levels to lead to high fatty acid production, but also the high NADH levels, they also promote the formation of the glycerol needed for triacylglycerol synthesis. So the high NADH, right, will come in, drive this reaction this way, and make some NAD in the glycerol 3-phosphate. And this glycerol is what's going to be included with the fatty acid to make triacylglycerol. Okay, so that's how that's occurring. And honestly, if you've stuck this far, I might as well just tell you all the other things that occur here. So when the citrate comes out, it turns into acetyl-CoA, but it also regenerates oxaloacetate, and the enzyme there is called citrate lyase, right? Citrate lyase, that's the enzyme there. And before going into de novo lipid synthesis, the acetyl-CoA must be turned into something called malonyl-CoA. This is required for the first steps of fatty acid synthesis. So the malonyl-CoA must be involved there, okay? And the enzyme that's, taking place here is called acetyl-CoA carboxylase. So ACC, acetyl-CoA carboxylase. I'll write it in this color. ACC. Boom, boom, boom. Okay. So we finished up with the hepatic steatosis there, or the liver steatosis. The last thing I want to talk about is vitamin A deficiency, and this one's kind of weird because vitamin A, specifically retinol, okay? Retinol can be converted into retinal, right? Inside of the liver. And it uses an enzyme called retinol dehydrogenase. But it's been thought that the retinol dehydrogenase is very similar. In fact, it's identical to alcohol dehydrogenase. So ethanol, which uses the ADH, can compete with the retinol dehydrogenase, preventing the conversion of retinol into retinal and causing a vitamin A deficiency. Okay? So that's one way. The other way, by the way, is that retinol, retinol can go through the cytochrome P450 system. It can, but if it goes through there, it'll actually be wasted. It won't actually be activated to active retinol. So when excessive alcohol intake actually induces this pathway, more of the retinol can be converted into this, directed into this pathway and become wasted. That's two ways that retinol is getting wasted, right? One via the competitive inhibition of ethanol with the retinol dehydrogenase, which is similar to the alcohol dehydrogenase, and the other one is the induction of the MEOS pathway. So that's how the vitamin A deficiency can also occur in these guys. All right, guys, so just to recap everything one more time, ethanol, 80% of it will be actually oxidized or metabolized in the liver, right? The hepatocyte specifically. It can take three different pathways, but the two main ones are going to be the alcohol dehydrogenase pathway and the microsomal ethanol oxidizing system pathway. This one's responsible for about 20% of the oxidation, upwards of 30% in alcoholics, and this one is responsible for the majority of it. But remember, it's got a high Km, which means that although it may have a higher affinity to the substrate ethanol, it actually has a lower capacity of oxidizing too much of it, and we said it gets saturated at around 15 to 24 milligrams per DL. Thus, when it gets saturated, it can no longer form acetaldehyde to put into the mitochondrion. The ethanol will shuttle into this MEOS pathway, right? And will form the acetaldehyde, and they will go into the mitochondrion, which will be turned into acetate using the enzyme aldehyde dehydrogenase type 2, which produces a lot of NADH. And we said that a high NADH to NAD ratio can actually shift the metabolism of the cell towards reduction in hydrogenation reactions to try and regenerate some NAD positives. What that means is the high NADH will inhibit the Krebs cycle, which, like I said, makes a lot of NADH itself, right? And if we're making a lot of NADH from the alcohol pathway, we're going to inhibit the Krebs cycle activity, and that'll cause citrate levels to build up. At the same time, we're making a lot of acetyl-CoA, which will combine with the OAA from the Krebs to give us higher citrate, okay? But mainly, it's the NADH inhibiting the Krebs cycle, building up the citrate. The high citrate will be exported out of the mitochondria, which then will turn into acetyl-CoA with the help of specific enzymes, and then it'll shuttle into the de novo lipid synthesis pathway, where it'll actually make excess fatty acids and accumulate inside of the liver, okay? And you know that these fatty acids, they can go out into the bloodstream as NEFAs or be incorporated into the VLDLs and then be pushed out. But in liver steatosis, there's actually more of the storage of fats that's occurring, right? We also said that the high NADH has some other impacts. It can affect the GPDH enzyme, which means that we're actually making a lot more glycerol to actually store with the TAGs. We're actually going to make a lot more lactates by affecting the LDH enzyme and pyruvate levels. We also said we're affecting gluconeogenesis by affecting this enzyme, glutamate dehydrogenase, right, which will deplete the alpha-ketoglutarate levels and deplete alanine and aspartate and all the other kind of amino acids involved in gluconeogenesis that alpha-ketoglutarate helps generate. And finally, we said that there might be some ketosis that could occur depending on the metabolic profile of the individual, okay? Alrighty, everybody, so that's going to be it for the video. If you enjoy the video, if you truly like it, if you learned something from it, please consider subscribing, consider liking, and I'll see you in the next video.